Hopefully you all saw my announcement the other day. I was scrambling yesterday to get all these announcements out, make sure people are aware, or the test outlines at least. I just finished making up the finals. I actually have to solve them. So I solved one though. I solved circuits, and that seems to fit in a reasonable time period. But I got to do dynamics and mechanics. So I'll see how long it takes me to solve them. I'll figure out if I want to do one part or two. Let's see. So there's a new folder here, final exam. And if you're in the course announcement, that should take you, that takes you right to it. But we're going to finish up some chapter 16 stuff this week. Yeah, the test for module 5, remember that's coming up. And I put that outline. So let me show you the outline here. If you want to do this, well, not if you want to, but let's see. Oh, that's strange. I thought 1, 2, 3. Yeah, I guess that is. Yeah. Simple projectile. Well, the outline's right here. It's fairly straightforward. I tried to give some examples. And then this review for the final. If you click that, this is a practice. It's basically a bonus. I got to check, make sure it doesn't show up in the grade book as an assignment. But this has some problems in it that are. Oh, all right. Well, apparently it thinks I'm a student with this link. That's weird. The homework usually don't do that. Anyway, this takes you to the review for the final, which has a few questions on it, which I didn't write in here. Let's see. Yeah, 10 questions total. But remember, those questions are multi-part. Well, some of them are multi-part. So you'll actually be answering, I think it's like, 6 questions from your textbook. All right, let's go back. Are there any questions before we continue? I know I'll probably talk more about the final, but I want to get through some of this chapter 16 material because I want to finish up at least a segment of it. And then maybe if we do, well, we'll see how much time we have left on the end of the week. Let's see. Oh, right. We were working on this problem here. The van moving along at 30 feet per second. All of a sudden it stops or it breaks. Wheels stop rotating and it skids 20 feet. So we're in the process of setting up equations so we can find the, let's see, magnitude of the normal reaction and the friction forces. Now we're not given the weight of this van or the mass of the van, so we're gonna solve this in terms of the variables in the end. Oops, my document camera closed. Whoa. A little better. All right. So what do? We drew our free body diagram, right? We drew our kinetic diagram, which is relatively simple because we know it's decelerating basically, well, it's accelerating backwards, it's decelerating. We have our dimensions. We set up an equation for acceleration, right? This is just from the basic uniform acceleration equations, right? And we got 22.5 feet per second squared. Now we go here, we have the sum of the forces in y equals 0, and we can see it consists of the normal forces and the weight. Sum of the forces in x is the mass times acceleration. The way we've drawn it so far, right? We have here there. Everything's acting backwards, so we'll see what happens there. And then some of the moments. Oh yeah, so I was talking about this term here. So angular. This is, again, remember, this term here is basically the rate of change of angular momentum, right? You've got mass, moment of inertia times the angular acceleration. So mass times this is taken from the derivative, right? Mass times velocity or angular velocity would be momentum. Mass times acceleration or mass moment of inertia times acceleration is rate of change of angular momentum, right? Oops. All right, so what do we have? For our moments, we've got a, if we're doing it about A, we've got, oh, and yeah, positive is counterclockwise, right? If we do it about A, we've got the weight acting at 5 feet. So we've got 5W, that's a negative. Plus 12NB, right? And this is a nice thing about taking the moments about that point. If we did moment about G, that's normally how you do a rotational problem, but you know, there's a lot more forces. So we'd have like 1, 2, 3, 4 terms that we'd have to worry about. By taking moment about A, we've only got 1, 2, 3 terms, right? And because technically, because the friction's in line with each other, we eliminate that term because that distance is 0, right? So we do have a force of B, but it's in line with point A. So that term goes away. So again, we wanted to put two terms instead of 4 terms if we had done moment about G. That's point G here. All right, so this is equal to, remember we said I alpha is 0 because I alpha represents the, this is the change in, I'll just write it in here and we can say it's 0. Right, there's no rotational component to this van. It's not rotating about its center of gravity. Let's see what else. Where am I? Oh, there I am. So we're going to have M for the mass moment of inertia. Sorry, for this term here, we're going to have mass times acceleration times a perpendicular distance. And that perpendicular distance about A is 4 feet. The other thing we know is that mu, well, the forces of friction, FA and FB, can be written as mu K NA and the force of B mu K NB. So the assumption here is, well, it's a good assumption. The coefficient of friction is the same at each wheel, right? Because it's dependent on the material and the surfaces. So, you know, rubber and the road on average are about the same. So also, the weight is mass times gravity. So this means that the mass is weight over gravity, gravitational acceleration, right? Remember, these are mass is a derived unit in US units. So we can take this information. Well, let me just add this up here. Let me number these. Oh, I did. 1, 2, and 3. So take this information. I'm going to plug this into 2. All right, so now we can write, I'm going to factor out the mu K. And I'm going to have NA plus NB. These. And then mass times acceleration. So I'm going to replace the mass with WG. Missing the Oh, you know what I want to do? I want you to notice here, NA plus NB, right? Is W. So I'm just going to rewrite this first. Right, which makes sense in the context of if you were doing this with any other, any other single object like a crate, single point of contact, you'd have one normal force, right? So all you're doing here, this makes sense. The normal force is equal to weight, equal and opposite to the weight, right? So now I've got that, and then I'm going to write, MA. Yeah, that's what I was going to do. So for M, I've got W over G times acceleration. Now this is kind of neat because the weight cancels out. And you can see that mu k is equal to A over G, which is 22.5 feet per second squared, divided by gravity, which is 32.2 feet per second squared. So you wind up with mu k what did I get? 6.9. Oh, that's why I rounded it. Basically 0.699. Or, I mean, you could say approximately 0.7, right? That's the coefficient of friction between the tires and the vehicle based only on that information. And notice everything canceled, right? All the other terms that we didn't know canceled away. Now let's look at equation 3 here. And let's let's put some information in, or let's rearrange that. I'm going to substitute in for weight. So let me just write this again. Equation 3, we've got minus 5W plus 12NB equals. So we're going to replace the mass here with W over G. So I've got 4 AW over G. I want to solve for the normal force, right? NB, you can rearrange this. We're going to have W over 12 times the quantity, 4A over G plus 5. Right, weight factors out of the terms. That's an A. If you put in the values for this, what do I have? We don't know weight. We do know A, G, or A and G. So this is 0.65 W. That's what normal force B is. I'm running out of room here. Let me get another sheet of paper. I'm expecting to go on page 2 here. I can fit a little more on here. Remember, NA plus NB is W, so NA is just W minus NB. So NA is just 0.35 W, right? Comes from this. ENS 218. is a 16.1. All right, now we've got the forces to figure out. So we've got the magnitude of each normal reaction. Now we got to get the friction force at each wheel. So F of B, for example, let's start there. It's just mu K times normal force of B, right? So this is going to be the 0.7 times the 0.65, 0.7 times 0.65. Yeah, 455. So here we've got, I'll write the numbers in. Let's see. Here's my mu. There it is. Four, 455. And then the frictional force at A is just the same thing, right? Mu K times the normal force at A, which is 0.35 W, 0.35 times 0.7. Yeah, it is 0.245. I rounded differently in my notes, so I got to do the. All right, so for the front, let's do the front ones. The normal force there are two sets of tires here. Right? We're looking at a side view here. So in and out of the page, there's this tire, and then there's the tire on the other side of the van. This tire and the tire on the other side of the van. When we did the analysis, we took the normal force. We're only looking at two of the tires. So really, you could divide this normal force by 4. So for the normal force at each wheel, right, we've got to divide that by 2. Oh, this is NB. Same thing with the frictional force. Since there are 2 front and 2 rear wheels. So yeah, the normal force in the front, what do we have? 0.455 divided by 2, we'll end up with, oh, that's the force. Oh, where's my, oh, there it is, 0.65. Yeah, 0.325 W. And the force on the front tire of friction. Now remember, we're asked for just the magnitude of the normal reaction and the friction force. So we're just asked for the magnitude here. Let's see, 0.227. I'll round it up to 0.228 because it was 0.2275. Same thing for the rear. Just divide those by 2. Let's do the 0.245 first. Oops. So here we've got 0.123 times the weight, and the rear 0.35 divided by 2, 0.175. This is a nice example physically. Obviously, the normal force is a function of the weight, but you can see it's not evenly distributed, right? We've got more normal force. This is not a negative. This is an equal sign. Or more of the weight, at least, is distributed on the front tires, which makes sense, right? In a braking scenario. Well, plus also the distances that this is really kind of in the context of the distances that the center of gravity is from each tire. And then the frictional force, right, again, on the front tires is more than the rear tires. Let's go to the PowerPoint here. There's some notes. Yeah. We already talked about angular acceleration in some of the moments. Again, we could have taken our moment point. We could have taken A, B, or G. It doesn't matter. It just, affects the equations we write. In fact, you might want to, well, if you have time, retry this problem using a different moment point. And this is the same thing, center of mass, G. You'd only get the independent equations, right? You'd have some of the moments equal 0 about G. All right, so let's look at this next problem here. This is a thin plate of mass of 8 kilograms. It is held in place as shown. Neglecting the mass of the links, what you want to determine is at that instant when the wire has been cut. Oh, what's going on? Oh, okay. At the instant when the wire is cut, determine the acceleration of the plate and the force in each link. So this is going to be cut, and at that instant, as it starts dropping, right? It's not going to drop straight down either. Notice that. It's not going to drop straight down. It's going to sort of go at an angle because you've got these links here. So let's sketch this out and see what the heck is happening. All right, I'm going to start up here in the corner. We've got this rectangle. And we got a center of gravity here, G. So I'm going to draw the force diagram first. That BC. Now these links are at 30 degrees. It's supposed to be the same angle, FDF. I'll put a little 30 degrees and 30 degrees. We have some lengths here, at least on the plate. This is 200 millimeters. And this is 500 millimeters. Now we've got the force of gravity to consider, right? The weight is acting straight down, but we're going to choose some axes here. We're going to choose an axis that's normal and tangential to the hinge point of rotation. I'm just going to autofocus this for a minute because it looks kind of blurry. Or I'm just getting old. So each of these has different components, right? We've got the forces along the links, and then we've got the weight. And obviously this is going to be 30 degrees as well, right? Let's draw a kinetic diagram to have room. I feel like I'm doing everything bigger than my notes, and that's why I'm taking up more space. Now, in terms of the kinetic diagram, we're going to look at the center of gravity here. And we're going to look at the mass and acceleration in our new axes here, our normal, and tangential. So let me draw out the main system here. What we're saying is positive is N and T. And let me choose a rotation direction. I guess I'll go this way for positive. Over here, we've got a mass times an acceleration in this direction that we're trying to, the acceleration of the plate and the force in each link. And what does this do? This helps us, oh my God. Right, remember we're looking at all the points of the plate concentrated at G, basically. This is also 30 degrees from the vertical. We can put dimensions back in here. This is 250, and then the center of gravity is going to be 100 each. I need bigger diagrams. So this is just drawing the free body and the kinetic diagrams. And the nice thing about doing this is that we can look at the tangential and the normal components relative to this initial point of the swing, right? What are we doing? Initially we're rotating it about these points, E and F, right? So we can look at this as sort of a rotational displacement. So when we look at the acceleration of the plate, or part A, we can look at the tangential forces and the mass times acceleration tangentially, right? So what are the forces in the tangential direction? Well, by defining this as the normal direction, we've basically eliminated FAE and FDF from our forces, right? And we're left with basically the component of weight, right? So here we've got 30 degrees. We've got a triangle like this. So we've got W cosine 30 for the force equals, and MA is going to be a similar situation. We've got mass times basically gravity. Well, sorry, this is the acceleration. We got mass times acceleration tangential. We can break this down later, but this is basically all in the tangential direction here, right? And so we can cancel out. Let me rewrite this. This is mg, right? I'll just write it over here. Mg cosine 30. Let's cancel out the m's. We've got acceleration equals gravity times cosine 30. So the tangential acceleration is 9.81 meters per second squared cosine 30. So for part A, the tangential acceleration turns out to be 8.5, we can say 0, meters per second squared. And that's at an angle of, depending on how I write my angle here, 60 degrees. 60 degrees down from the negative horizontal, right? Which is just this, this direction that way. So, you know, we know the plate has to accelerate that way because that's how it's confined by these rigid links. All right, so part B is determining the force in each link. So the first part was just sum of the forces equals MA. Now we're going to do a little more detailed analysis. We're going to look at the normal component, and we're also going to look at the rate of change of angular momentum, right? So the first part is just, again, sum of the forces in normal is mass times normal acceleration. Now, notice we didn't have a normal acceleration, right? So that's just 0. So our sum of the forces are FAE plus FDF minus, so again, this is the nice part about choosing these normal and tangential components, right? You don't have to deal with at least we don't have to yet deal with the components of these vectors, right? These force vectors. Those are the forces in those links. And then we've got the weight. So the normal component of weight is going to be negative W sine 30, right? I'm just going to number this equation 2. And we'll hold on to this in the background. Next, I want to look at the sum of the moments about G equals I alpha. So again, alpha is angular rotation or angular acceleration about the centroid, right? And I chose this direction as positive. So just so you know, our directions are a little different than normal. There's no angular acceleration. This plate is not rotating about its center of gravity. So this is 0. No centroidal rotation. Let's see, can I fit this in? No, I can't fit it in anywhere anyway, so I'm just going to make it 2 lines. All right, so let's look at each of these components. So now this is what I was talking about with the band, right? We have to break each of these down, each of these forces into their x and y, well, their components with respect to g, right? The distance g. And we have, because of the dimensions we have, we've got 250 millimeters from A to G and 100 from, you know, A to G and D to G, right? So it's right in the center. So I'm going to write out the sum of the moments, and I'm using this clockwise direction as positive in this scenario. So we've got FAE cosine 30 gives us this component, right? And that's going to be directed this way about G, perpendicular distance of 100. So let's write negative FA E cosine 30 times 100. Let's look at Let's just look at the other component of FAE now. So the other component of FAE is directed upward, right? At that point, it's directed upward, and that's a distance, perpendicular distance of 250 millimeters. So that's the sine component. So that's a positive. What did I say this was? 250. I'm going to go to the next line here. So that's FAE. Then I've got FDE, or sorry, DF. FDF is going to have the same thing, and the X component is going to be trying to induce a clockwise rotation about G. So that's going to be a, oh wait, G, FDF. Looks like I messed up a sign here. Yeah, that's definitely counterclockwise, and that's, oh no, wait. Okay, yeah, we're below. All right. Sorry, this is above, this is below. So above this, we're going, yeah, we're rotating about G. Above this, we're going this way. Below it, we're still going this way. So below, the points below here are going to be inducing a clockwise rotation, which I forgot. I changed my sign, so it's positive. So we've got plus FDF cosine 30 times 100. And then we've got the y component of FDF, which is the same as above. Right. So these are all moments about G. So watch your signs. I actually started to confuse myself for a minute because I chose the opposite direction, so I was thinking the opposite way that I normally think. But that's, well, the way I normally think, right? So now we have an equation that we can sort of lump together here. If you take the cosine of 30 and times 100 and the sine 30 of 250, you wind up with some numbers. Let's write this all out. We've got minus 86.6 FAE plus 125 FAE. And then I've got another FDF, right? So same thing, plus 86.6 FDF plus 125 FDF. And this all equals 0. Yeah, did I forget to write that? This is 0. Some of the moments about G is equal to 0. So let's see, I wind up lumping terms here, and I get 38.4 FAE plus 211.6 FDF equals 0. I can write these in terms of one another. I can write FDF and FAE in terms of one another. I've got a negative 0.181 FAE. So my equation 1 was actually up here. So I've got 3 equations here to use. We're basically going to stick with these 2 in this component, this part. And so if you're wondering, that was just if you're wondering how I got to 3, I've only got 2 equations. I had forgotten to label that equation 1. So we take 3 and substitute it into 2, right up here. We wind up with FAE minus 0.181 FAE equals W sine 30. So you wind up getting 0.819 FAE is equal to W over 2, right, sine 30. You can continue this on and find that FAE is 0.611 W. Remember, W is mass times gravity, which is 8 kilograms times 9.81 meters per second squared. This gives us 78.84 newtons. All right, so this is FAE, and notice FDF is negative of FAE. Now, let's write this out here. FAE is 78.84 times the 0.61, so we've got 47.95 newtons. Now notice the directions. This came out positive, and we chose, or we're treating it as positive in that direction, right? So we can say that FAE is under tension. Now, the other one, FDF, if I take FAE and I plug that in here, I'm going to wind up with a negative, right? So I'm just going to write that as 8.71 newtons. Now I'm going to recognize that it came out negative. It came out negative even though we treated it as in tension, right? So that means that it's in compression, so it's in the opposite direction. So we wind up with 47.9 newtons in tension, 8.71 newtons in compression. Let me go back to the picture here. So we're saying the top member AE is in tension. The bottom one's in compression. Right, and that makes sense. As this is cut and this is released, it's going to want to sort of swing down this way. Well, it's going to go this direction. And what's it doing? Well, if these were, it sort of wants to hinge around A, right? It wants to pull on A, and it's compressing on D, right? In that scenario, because it wants to sort of swing down, but it can't. It wants to tilt. In other words, imagine A was gone, right? This would just sort of flip down like that. And imagine D was gone, right? It would also rotate about A like that. But it's not. We've got two points, two linkages. So it's staying stationary and just sort of, moving down like this. Well, it's technically in a straight line direction because of the linkages. Any questions about this problem? Let's see. We want to actually get through a bunch of stuff here. I think what I'll do is it's 9:45. I'll just end, unless you guys have questions specifically about something. Oh yeah, this is an interesting point, right? If these have been cables, you can't have a cable under compression. This would have just gone slack, right? And again, they're just saying here you could have chosen any moment you wanted to. So that's what I have. Let me stop the recording, and then if you have a specific question about something,